Hello everybody, here's a brief introduction on linear approximations. If we take a look, let's say up here, if we have a function and it's differentiable at a certain point, what's the equation of the tangent line at a certain point? So we've been seeing this come up over and over again, right? So this is just another way of finding the equation of our tangent line. Please remember what we know so far. We have a point, some x value in f of x, and then we have a derivative, and of course that derivative is our slope. Please recall our point-slope formula. Now watch what we're going to do. We're going to do some substitution here with the information we have on the left. All I did here was notice, see y1, isn't that the f of a? So I plugged them in here. See my slope, isn't that really the derivative of a? So I plugged it in here. And see my x value, isn't that truly a? I plugged them in. So that gives us a formula that looks like what I just wrote in blue. And truly, that is just the point-slope formula. Now notice one more thing. I'm going to isolate my y here. All I did was add the f of a to both sides. So truly, this is still point-slope form of a line, is it not? So check this out. This is our formula for linear approximation, or the equation of our tangent line. It's an approximation. See this formula up here? Instead of y, we're just going to say f of x, or for linear approximation, we're going to say L of x. See this f of a here? I'm going to bring them down here. And see the rest of the equation? So truly, this is just another form of point-slope form. Let's go ahead and do an example. Please take a look at example 1. So they want us to find the linearization of this function at a is -1. So let's go ahead and plug this into this function here. All I did was plug a, my a value, into this function. Did I not? And when I compute this, now let me point out, the way I got this next step was just over in my notes. I figured out, okay, what's the f of -1? I plugged -1 into this function and I got -11, okay? What's the derivative at -1? I took the derivative of this function. Here's the derivative, and I simply plugged -1 into that to get my f prime at -1. Is that okay? So there we go. And from here, we can go ahead and get our linearization. Let's see, we'll have 14x plus 14 minus 11, that'll be plus 3. Okay, so here is our function. This is the equation of our tangent line at a specific point. Now check this out. They want us to compare these two values here. So let's go ahead. We could plug this value into our function. Go ahead and pause it and plug it into your calculator. And then they ask us to also find the L of the same value. So of course we're going to plug it into this function right here, which is basically the new part of our lesson here. And look how close these are. Super duper duper close. Within 10,000ths of a decimal place. Not exact, it's an approximation, but still pretty effective. Okay, so what we're teaching you here is this. Now, for example 2, This example is a bit more complex, but let us do this again. Let's use our linearization and plug in a of 0 this time, right? There you have it. Let's go ahead and solve for g of 0 and for the derivative of g and for the derivative of g at 0. I'll do that in green. So here, up here is our g of 0. We'll plug that in here. And now let's go ahead and take the derivative of g. And then we have to find out the derivative of g at 0. So I'm just going to plug 0 into that guy there. And we should get, we'll get 1/3 because our parentheses will just be 1. So plugging in for our linear approximation, here is our equation. All right, now let's go ahead and take a look at this. They want us to give our approximation for the cubed root of 0.95. Now, be careful about that. This part is a little new, and I'll write this in red. Notice this was the original function they gave us right here, true? But they want us to approximate 0.95, the cubed root of it. So be super careful, because how do we write 0.95 in this form? It would look like this, would it not? So this is a little bit tricky, but if you look here, the x value is 0.05. Yes. So truly, we need to look for the g, excuse me, it's negative 0.05, right? We're looking for the g of negative 0.05, which our linear approximation will give us a very close value to that. So what we have to do now is we have to plug 0.05 into our equation that has the green square about it. Okay, so what does this mean? We were able to approximate this number right here, what this value is. And if you were to type that in to your calculator exactly, if you were to type this into your calculator, you would get something like this. And look at how very close that is to each other. Number 2 is much of the same thing, and if you don't mind, I'm gonna fly through this one. Please just notice they gave us this value right here, and this value in the denominator, 4.002, is super close to 4. So we're going to approximate our function very close to a equals 4 here. I'm just going to write down all these derivatives and stuff. Just explain this part as well. We weren't given a function in this case, so it looks like our function would be super close to that, right? 1 over x or 1 over some number. So we're going to take the derivative of that. We have our derivative. Now we're going to plug in 4 to both the function and the derivative. And we'll get that. Now we are going to plug both of these into our linear approximation equation. From the first page, we know it will look like this. And we'll have this for our approximation. All right, now in blue, let's go ahead and solve this problem. So we are looking for, I promised blue, here we go. So that's going to be about 1/4 minus So we were able to use the linear approximation to use this fraction and approximate what it equals. Hope you found it helpful.